The expected value of an experiment is a probability-weighted average of all possible values. To calculate the expected value for an experiment, you take each amount to be gained or lost times the probability of that amount. For the first example, a toll collector estimates that the number of passengers in cars during the morning rush hours varies from 1 to 5 with the following probabilities. We want to find the expected number of passengers per car. So to find the expected value, we'll take each amount times the corresponding probability. So the toll collector observes one passenger in the car 21% of the time, two passengers in the car 33% of the time, three passengers in the car 26% of the time, four passengers in the car 12% of the time, and five passengers in the car 8% of the time. This comes to an average of 2.53 passengers per car. So it's an average in the long run. For a second example, for an outdoor concert, event organizers estimate that 20,000 people will attend if it is not raining, and only 12,000 people if it is raining. On the day of the concert, meteorologists predict a 30% chance of rain. We want to determine the expected number of people who will attend this concert. Well, the probability of rain in decimal form, if we drop the percent sign, move the decimal point 2 places to the left, is 0.30. To calculate the probability that it will not rain, I use the complements formula. That is, I'll take 1 minus the probability that it will rain. So it's 1 minus 0.30 or 0.70. So to find the expected number of people who will attend this concert, we'll take each amount times the probability of that amount. Well, the first amount was calculated was estimated for when it doesn't rain. And what we figure is that what the concert event organizers estimated was that 20,000 people will attend if it doesn't rain. The probability that that will happen is 0.70. If it does rain, the event organizers estimate 12,000 people. And the probability that that will happen is 0.30. That gives us 17,600 people. So sometimes it rains and there's only 12,000 people. Sometimes it doesn't rain, there's 20,000 people. This is the average of the number of people in the long run. Now for number 3, you're at a carnival and you see a game. For $2, you roll a standard 6-sided die. If the number showing is a 6, you win $10. Otherwise, you win nothing. If you're trying to make money, is it in your interest to play the game? Well, let's find the expected value. First of all, the cost to play. That's $2. prize is $10. To win, I'm going to roll a 6 on a 6-sided die. Now the probability of winning, there's 1 6 out of the 6 sides on a die. So the probability of not winning is 1 minus the probability of winning. So 1 minus 1 6, or 5 6. All right, so when we go to play this game, you can either roll a 6 or not. You can either win or not. Now, if you win, you're really only gaining $8 because the carnival host is not going to give you your $2 back. So the probability that you'll gain that $8, since you're not getting your $2 back, is 1 out of 6. If you don't win, he keeps your $2. The probability of that happening was 5 6. So I have 8 6 minus 10 6 equals a negative 2 6. In terms of dollars and cents, it's a negative 33 cents. So is it in your interest to play this game? No. On the average, you're losing 33 cents per game. So is it a fair price? Absolutely not. You're losing money. It's only a fair price if the expected value is 0. So neither the host of the game nor the person who's playing the game make any money. You're just playing for fun. A fair price to pay to play this game is the expected value plus the cost to play. The expected value was negative 33 cents. The cost to play was $2. So a fair price would be $1.67.